For those who are attending SEMLA for the first time, allow me please a bit to introduce what is SEMLA. So SEMLA is a forum that aims to bring together both researchers from the software engineering community and the machine learning community to discuss about the challenges of implementing and building machine learning-based systems. So this is the third edition, and we have been blessed to have leading experts from both machine learning and software engineering interact in this forum, and we hope you're enjoying this so far. Well, so we are the organizers. So SEMLA is organized by faculties at Polytechnique Montreal. So Professor Adams, Antonio, Cheng, Fokaes, myself, and Professor Nahebi. We have been running this normally on site, but this year, given the pandemic situation, we decided to opt for online webinars. So the program of this year, it's composed of 6 talks. So we already have 2 webinars last week from Diego, who is the founder of Algorithmia, and from Professor Kastner from Carnegie Mellon University. So this week, we have 2 more exciting webinars coming ahead. The first one, which will be starting in a few minutes, from Samuel Deng from Columbia University. It's a joint talk. We've done work with Professor Vadi from Columbia University as well. And tomorrow, we will have Gradibut, who will be presenting us the webinar at noon as well. So Samuel Deng, it's a researcher from Columbia University. He will approach the issue of bias and fairness from a philosophical point of view. And I think this will be a very exciting perspective to hear from Samuel Deng and Professor Vadi work on how, on a philosophical aspect, they understand the challenges that we are facing in ensuring that we are building machine learning-based systems that are not biased, and that is fair for all the users. So without further talking, I will set the floor to Samuel Deng to introduce the talk. So similar to the previous edition, we'll be using the QA to collect the questions. So if you have any question or two at the top, so just feel free to write in your questions. And please vote on the questions that you find to be the more popular. And we will start the QA discussion session by picking those questions and continue as the discussion progresses. So I will stop sharing and please go ahead, Samuel.
Cool. Thank you so much for the introduction. So let me get my thing shared up. Yeah, so thank you so much for the introduction. As Futsi said, I'm Sam Deng. I'm an MS student currently at Columbia University and a researcher in the computer science department. And I did my undergrad in philosophy and computer science. And I worked with Professor Akhil Varzi of the philosophy department at Columbia University on this project. Methodological blind spots in ML fairness, lessons from the philosophy of science, and computer science. And we'll be publishing the slides, I think. So I have an archive link for the full version of this, of a workshop paper of this. And that's right here in the bottom left corner if you want to check it out for more. So yeah, without further ado. So yeah, first of all, what's like the motivation or the vast motivation for this project? As many of you might know already, there's been a recent huge explosion in AI and ML ethics and fairness over the past, I'd say, like couple of years. And this is like basically concerned with algorithms that are biased or have discriminatory effects on certain populations. And so this is both in like academia and in media, right? So algorithmic decision-making and using like statistical models trained on data to make predictions, it seems like a compelling way to ensure that decision-making by humans is accurate and fair, because humans might overlook many of the patterns that machine learning might find in data, right? And it seems objective to kind of base outcomes on data. And that was the original kind of motivation for implementing machine learning algorithms in high stakes decision-making scenarios, right? And on the academia side of it, there's been actually a fair amount of, I guess, growing amount of papers in the ML fairness literature, there's like actually an explosion of like ML fairness algorithms and like techniques to kind of ensure fairness every year. There's like a brand new conference, Fat Star, which I think started a couple years ago in 2017, I believe, that researchers are now just completely, I guess, tuned in to like ML fairness. So this is exclusively for like ML fairness. There are also sub conferences for like pretty mainstay ML conferences like AAAI and ACM for Artificial Intelligence, Ethics and Society. And for NeurIPS this year, which I'm sure many of you know is like one of the main ML conferences or biggest ML conferences. There's even this section that authors had to this year write a broader impact section on how their algorithms or their ideas, their papers kind of had a broader impact on society, or their positive impacts on society and their negative impacts on society. And that was actually mandatory for a lot of papers if you wanted to submit one this year. So that's on the academia side. There's like a growing literature in ML fairness as a subfield itself that is hard to ignore on the academia side. And also in the public eye, I'm sure that you might have seen at least one of these articles in the past like couple of years where we're talking about machine learning systems that are biased against certain individuals, right? This one over here, machine bias, that one is probably the most prevalent or famous. It kind of kickstarted this whole thing. And I guess all ML fairness talks are kind of remiss if you don't mention this article. But this one is about a recidivism prediction software that we're going to go over later in more detail called Compass, that basically had the job of assigning statistical scores to individuals to inform their likeliness of committing another crime. And this score affected many decisions such as like bail and sentencing and parole. And it was biased against Black individuals. And so there's other, I guess, headlines that you see all the time in the news about like facial recognition systems being heavily biased or discriminatory and just less accurate against minority populations versus white populations, and I guess headlines on like hiring algorithms being gender biased, etc. And you see this all the time, and it's even prevalent if you're not in contact with any of these systems on your day-to-day, right? Because you're browsing the internet and there are recommendation systems that are obviously powered by ML and search engines and ad targeting, and all of this stuff kind of shapes our cultural and information diet. And all of these also take demographic information into account. And yeah, so a huge explosion in this kind of stuff in both academia and the media. And so the question is kind of what we could do to kind of help. And so the motivation for like the actual paper specifically is to use philosophy to kind of maybe try to combat this. So at first glance, it seems that like the ML fairness literature is a pretty rich field for philosophy to get its hands on, because it seems like philosophy deals with the same issues as ML fairness might be concerned about, right? Issues like normativity or ethics or fairness or justice, they're all in the realm of philosophy, right? But when I first started my investigation into this, there was actually surprisingly little from the field of philosophy that was concerned with ML fairness. There's actually surprisingly little literature from philosophers thinking about this, right? So I decided to take a stab at it. And I guess the whole like point of philosophy, or like one of the main points of philosophy, is to kind of just like tease out basic assumptions. That's like one thing that philosophy is very good at, and kind of sanity check what we take for granted, and kind of define elusive concepts like justice or fairness, ethics, into terms that we can actually look at and argue about, right? Clearly. And so that's what we're going to try to do today. Possible questions that philosophy might answer that we're not going to go over, right, is stuff like what even is fairness, right? And what definition of fairness is best? And philosophers have been arguing over this for years, centuries now, right? And it's an unsolved question, right? So we're not gonna solve it today. But instead, we're gonna we're gonna try to use philosophy, or just philosophy as a framework, to kind of tackle a lot of the assumptions that are underlying ML fairness, and see like if there are any blind spots that we might be missing if we're not like taking a step back and looking at it from this viewpoint. So Yeah, our goal is instead to kind of tackle some philosophical questions that underlie the practice of fair ML that might go unnoticed by researchers in ML or software engineering, or ML engineers that are in the field, most importantly, just actually doing this stuff in the wild, right? And so kind of test run whether philosophy is a useful tool for exploring ML fairness, and taking a step back and looking at the basic taken for granted assumptions that underlie ML fairness in the light of philosophy. So that's kind of our goal today and our motivation. And it's just kind of like a high level test run to see what this might look like for ML fairness, and to kind of hopefully encourage further work from philosophers and domain experts outside of ML. So, okay. So we're going to be going over 3 blind spots today that you might have seen from the title. So by blind spots, I just kind of mean, like I said before, like assumptions that we might take for granted when we're building ML systems, researching ML systems, creating ML algorithms that pertain to fairness. And we're just going to try to like define them a little better and kind of tease out what might be wrong with them and what you might be cautious about when you're creating these systems. So the first is abstraction. This is a value from the philosophy of computer science. I'm sure that many of you know. And this is basically what we're talking about when we're talking about what's lost when we translate from normative philosophical definitions of fairness to mathematical abstractions and code. And this has to do with kind of modularizing values that we have that seem elusive and kind of undefined, like fairness, justice, things like that. And a lot is lost in translation when we switch context and we try to translate messy and unsolved normative notions that are in the realm of like philosophy and sociology into mathematical formulations. The second is induction. So this is a very crucial, I guess, problem in the philosophy of science. So induction is concerned with what are the philosophical issues in the process of just inductive decision-making. Inductive decision-making being generalizing or making predictions based on past data. And yeah, inductive decision-making itself is obviously at the heart of ML, right? Because that's the whole point, is we generalize on past training data to make predictions on tests, right? But induction itself has a really large hole in it when actually philosophers look at it. And it's still kind of unsolved. And this is via Hume. We're going to go into this later. Yeah, in the context of fair ML, it's especially interesting because the data itself, past data, might not have all we need to make a fair algorithm in this sense. And finally, we're going to talk about measurement, which is also which is closely related to abstraction, and it's related to how we kind of translate messy empirical notions into formal mathematical notions. And this is also a mainstay in the philosophy of science. And so we're going to ask basically what we take for granted when we're given a data set of measured features and outcome variables, and what some pitfalls there or blind spots there might be that you might not see if you didn't approach it from this standpoint or perspective. And so, yeah, these are like the 3 blind spots we're going to be going over. But before all of that, we're going to be going over the field of value theory, which is, I guess, a broad field in philosophy, or I don't know if you even want to call it a field. It's a broad definition that encompasses a lot of moral philosophy, political philosophy, and aesthetics, and other fields. It's easy to understand what a value is intuitively, right? It's basically anything that has an evaluative notion. So what things that are good or bad, or how good and bad are things. So any value that we might talk about in these branches of philosophy, like moral philosophy, political philosophy, or aesthetics, they all conform to the question, how X is this thing? So if we're talking about the value of like justice, which is probably one of the ones that was argued about probably most earliest in philosophy. It's how just is this law? We might ask, how just is this constitution, right? Things like that. How just is this ML system, right? And then if we're talking about the value of beauty, right, in aesthetics, we might ask, how beautiful is this painting? How beautiful is this piece of music, et cetera, this composition? So pretty simple, but this is a lot of the work in philosophy, in moral philosophy and aesthetics, kind of deal with trying to well define these things and try to narrow them down into better, more arguable kind of frameworks. So yeah, all aspects of philosophy kind of conform to asking what goodness of some sort means, especially moral philosophy and aesthetics. And the goal is to kind of formally define and argue about the goodness of certain values, right? So what does it mean to be just? Like, what does justice mean? And what does it mean to be beautiful? What does beauty mean? There's also, I guess, fairness, right? But we're not, like I said before, we're not going to try to answer like, what does fairness mean? Or what's like the best definition of fairness? Because that's yet hotly debated, right? But yeah, what we're going to try to do is just at least narrow down the value of fairness in the context of just fair ML. So a literal subsection of that. And we're going to try to make an assumption on the value of fairness in the context of fair ML or fair machine learning. And we're going to try to make a simple and intuitive assumption on how ML fairness is kind of context sensitive. So I'll explain that. So context sensitive value. So we're going to make a pretty intuitive definition here on certain values. And basically, we're going to define what a context-sensitive value is as a value that yields different evaluations depending on the surrounding context. So it seems intuitive that some values are context-sensitive. There are values such as usefulness, for example. You could obviously ask an evaluative question for that. How useful is this thing? How useful is this hammer or whatever? But it seems intuitive that an object's usefulness depends on its surrounding context, right? The usefulness of a chair that's in a bare room is obviously less useful than a chair at a dinner table, the last chair at a dinner table. Clearly the latter is more useful, right? But in both contexts, right, the evaluation of the value of usefulness is different, right? So this seems pretty intuitive and pretty, like, why would I even say this, or why would I even argue this, right? But I argue that in fair ML, in fair machine learning, right, the fairness of a particular ML system is very dependent on its context, right? It's dependent on its societal context or its application domain or the training and test data or the stakeholders involved or the algorithms involved. All of these things kind of factor into evaluating the fairness of a particular ML system. And this is pretty intuitive because if you look in the fair ML literature, a lot of it is, if you've seen any of these like papers that have group fairness definitions, like these statistical fairness definitions, one common one is false positive rate parity. Or equalized odds is a common one. False positive rate parity is a relaxation of this. So this whole definition is equalized odds, where you equalize the true positive rates between groups and then the false positive rate between groups. So A equals A might be, A might be, I guess, male individuals, and B might be female individuals. And this is basically one way that researchers in FairML have thought of constraining fairness in terms of algorithms or kind of evaluating fairness. So yeah, one example of how fairness could be context sensitive is if we're implementing this definition, right, of false positive rate parity, just the bottom line, right? The false positive rates are equalized between groups. For hiring, for example, like job hiring, a false positive where someone that's unfit for a job is employed has about the same harm, if not more harm, I guess, than a false negative where someone fit for a job is denied. Because an unfit accepted applicant might just get laid off after giving the company some value, while there's really no second chance for an unaccepted applicant, right? But for recidivism, again, predicting whether a defendant might commit a future crime, the false positive of wrongfully putting someone in jail might propagate an existing injustice that we might not want in the context of fair machine learning, right? And this might perpetuate higher populations of certain minority groups being sent to jail, and this algorithm being used for things that are contrary to what we might want to establish in fair ML. So yeah, it seems intuitive that fairness in the context of fair ML, the field of fair ML, right, is context sensitive because of these things, because different stakeholders and different contexts of using the same algorithm or the same fairness definitions, right, could be wildly different in different scenarios. So that's a context sensitive value. And so we're going to move on to the first kind of blind spot of fair ML. abstraction. So for abstraction, we're just gonna kind of look at, we're gonna kind of ask what's lost when we translate from normative philosophical definitions of fairness to mathematical abstractions and code. So abstraction itself is a fundamental tenet in computer science. It's probably the first thing that you learn when you learn how to like build systems or like do software engineering, right? It's that systems are made up of modular, well-specified components, right? And measurement is also a very important aspect in abstraction, that we could translate, I guess, empirical concepts that we see in the world into just mathematical or like numerical values that we feed into ML algorithms, but gets that later as its own kind of blind spot. Yeah, but the goal often is for ML systems in fair ML is to, they're concerned with modeling messy, often human phenomena with mathematical abstractions, right? When we're talking about fair ML algorithms, they're usually concerned with decision-making in very human scenarios, right? Bail or recidivism or hiring or facial recognition, right? It's human phenomena that have to be translated into mathematical abstraction. And that also has to do with the definition of fairness, right? Like we said before, definitions in one context might not work for another. Here are like a bunch of definitions like that are prevalent in the fair ML literature. And for instance, if you've seen any of these before, demographic parity is one definition where it equalizes just the positive rates between groups, unconditioned on anything else. So conditioned on a certain group equalize the positive rates of the classifier giving a 1 or a positive outcome on individuals. Whereas equalize odds, like we said before, equalizes true positive rates and false positive rates for all groups. Over here, I guess. And false positive rate parity that we saw before just equalizes true positive rates or false positive rates for all groups, right? So ethics itself isn't really a closed field, like we said before. So how can we assume that one abstract definition captures all notions of fairness? And the answer is that we often can't, right? The goal is to often do the math of fairness, right? And to manipulate mathematical definitions and say that an algorithm is fair once that we've subsumed a mathematical definition on that algorithm, right? And it's tempting to now, if you do that, to export them to different contexts, right? To kind of say that something that's fair in one context is fair in another context. Or once we have said that it's fair using some mathematical definition, that it is fair down the line in any further systems that it might influence, right? But that's often not the case, because there's often trolley problems in ML, like the one that we just discussed before. Like, what does it mean? Is it more fair to kind of equalize false positives? Is it more fair to equalize false negatives? Is it more fair to just equalize positive rates for both groups? Or other fairness definitions that maybe kind of pertain to individuals, like individual fairness is another fairness definition where each individual has a distance metric between each other, and fairness is kind of optimized that way. So yeah, this plug and play kind of mentality that fairness could be subsumed or encapsulated in one mathematical definition kind of conflicts with context sensitivity, right? That fairness itself in fair ML is context sensitive as a value. And yeah, so there are these trolley problems where we can't decide between one thing or another. And one example where this happened in real life, I said we were going to talk about Compass and ProPublica in that article because it's kind of like required for all ML fairness talks to talk about this one. But like Compass versus ProPublica was a big case that kind of kickstarted this whole ML fairness literature. Like was one of like the first articles that came out in the mainstream. And basically what happened was that a company named Northpoint, I believe, had a widely used data-driven algorithm named Compass. It was an ML algorithm that predicted recidivism, or the probability of committing a future crime again. It was used widely in like criminal justice settings, from sentencing to parole. And so ProPublica, a social justice-oriented like newsroom, had an article on that basically evaluated this algorithm, and they said basically that was unfair to minority individuals, particularly Hispanic and Black individuals in a lot of the communities where Compass was used. And their fairness evaluation of it, right, used the false positive rate parity as a criterion for fairness. the one that we just mentioned before, that we equalize false positive rates between groups. While North Point pushed back, saying that their algorithm was fair, and it was fair in the sense of another fairness definition, right? Calibration by certain groups. But they were both arguing that the algorithm was fair or unfair, so who's to decide, right? And you can see that something gets lost here in the math of doing the fairness, right? That kind of finding a fairness definition for one evaluation might not play nicely with the fairness definition of another, right? And so that was like the conflict there. And two abstractions of fairness lead to obviously different views. So yeah, we're gonna also go over a couple quick things with abstraction that might also be overlooked, right? So these kind of have to do with philosophy of computer science as well. So central to computer science is like the ideas of specification and modularity, right? When we're designing software systems, right, this is pretty important, right? To well specify something, a component of a system is just saying, given some inputs, like the outputs are well specified, and we could just kind of treat that as like a black box, right? So for instance, if I make an algorithm that squares a number, then the input x, we give it an input x and output its square, x squared. And we could trust that it works fine in downstream tasks and further down the pipeline, right? But in FairML, this might be, or this might not be sufficient, right? Because an algorithm that gives quote unquote fair outputs, right, might only be fair with respect to some fairness criterion. And so using this specified system that it's fair down the line further. So maybe like if I'm using recidivism scores from Compass to inform decisions about bail or parole and things like that further down the line, right? This might influence further. This assumption that the system or this part of the system is fair might influence things further down the line. That might assume that it's fair, where it might be only fair in one sense of the word, right? Like we said before. So, and also, so what is kind of a solution for this? Thinking of things as better specified if we include domain experts and kind of philosophers or sociologists in kind of the pipeline of specifying things, right? And having humans in the loop could assuage this kind of conflict or problem. To make sure that things are fair with respect to how we want them to be fair, right? If we want the normative assumption to be that we want to equalize false positive rates, because assuming that false positive rates, equal false positive rates are acceptable due to some moral motivation for maybe long-run diversity between groups A and B, right? Then we might want to use a false positive rate definition, but only then, right? And understand that these abstractions and these specifications are fair only in one sense of the word. So also modularity. It's also obviously a tenet of software engineering and computer science, right? That things are modular, right? And that a lot of times problems in ML in ML engineering, right, are characterized by like the nature of the learning task or established methods that we might use on them, like SVMs or neural nets, and some optimization problem, right? And if obviously you've done any type of like ML engineering before, right? Like, you know that it's pretty easy to like make a pretty state-of-the-art model, right? Like you just do single line imports to guarantee a fair, to guarantee some classifier, right? So like import scikit-learn as sklearn, model.fit, model.predict, right? And a lot of it is abstracted away, right, as black box. But there are increasingly, like plug and play, this kind of modularity is increasingly necessary for complex systems, right? But I argue that it kind of conflicts with context sensitivity as well, right? Because something that's fair in one context, right? If you kind of put fairness under the hood and you just, and this has been done in a lot of like software packages now, is like guaranteeing a fair classifier is often done with just like maybe wrapping a classifier with some fairness class or something like that, right? Something that's fair under the hood, that kind of assumes fairness under the hood, might be used in other parts of the system, right? And in other parts of the system, that might not be the same definition of fairness that we want, right? So this abstraction and modularity, right? This plug and play might kind of be contrary to what we want, what we really want in fair ML. So that's a little bit of blind spot there. And yeah, that's abstraction, I guess. So yes, I think that's all I want to say about that. So second, we're going to go over induction, which is the second thing that we're second blind spot that we're going to go over. So induction is a very central problem in the philosophy of science, right? Over here, this is David Hume, who first posed the problem of induction. And basically what an induction itself is pretty simple. It's that future events, it's the, I guess, like process of predicting future events that we've not experienced or observed to observed events that we have experienced, so past events, right? So if I drop a ball 100 times, I might expect that, and the ball falls down, right, to the floor. I might expect that the 101st time that I drop that ball, it's going to also go down. It's not going to go up or anything, right? But one very central problem in the philosophy of science that has more or less been like, has been tackled a bunch of times, right? And been brought up a bunch of times, but hasn't been, I guess, solved, is the problem of induction via Hume. So Hume famously argued that there's no necessary connection between observations that we have and unseen events in the future, right? And there's actually nothing necessitating the fact that future events might, I guess, future events might be influenced by the by past events that we've seen. Okay, and this problem of induction has been at the center of epistemology and philosophy of science since like about the 18th century. And of course, this is at the center of ML and science in general, right? Because because ML is just interested in the process of generalizing and kind of making predictions and general rules from historical examples, data, right? And this has some interesting implications in fair ML in particular. If we think of it just, if we think of fair ML kind of from this starting point philosophical perspective of induction and how induction might not be so trustworthy some of the time, or necessarily trustworthy. Yeah, and if you're interested then in reading further on this, then I would just suggest reading Hume directly on this. Pretty nice, I guess, book on this. And then so one more modern approach to the problem of induction is Nelson Goodman's riddle of induction. So Nelson Goodman is also a philosopher that posed this same, posed a problem in induction that he put in the form of a thought experiment, right? So I'll just give you a brief summary or like basic version of the thought experiment now. It's that, so suppose up to like time t, or like now, we've observed many green emeralds. So like, yeah, green emeralds and no emeralds other than green ones, right? And so the first hypothesis that might be pretty self-explanatory or intuitive is that all emeralds are green, right? Pretty self-explanatory, and it seems pretty supported by our data so far, right? And then we might introduce a new predicate called GRUE, I guess, GRUE. And so we say that an object is GRUE if observed before time t, that object is green, but after time t, or now, the object's blue. So from the observations we made before, we could make a second hypothesis, and it's equally supported by the data, that all emeralds are GRUE, right? And obviously, by what we know about the world, I guess, or maybe, it's intuitive that all emeralds are green is probably a better induction, right? But with just the data and the hypotheses at hand, all of our data up to time t equally supports both hypotheses, right? Like there's nothing that necessitates that the next emerald is green, right? But all of our data supports that the emeralds are GRUE or that they're green pretty equally. So yeah, how do we decide from the same kind of set of data which hypotheses to accept, right? And that's our question here. That's Nelson Goodman's question, right? And one possible solution to this riddle of induction is Occam's razor, which is also a concept in philosophy, but it also kind of seeps its way into ML in learning theory, right? So basically Occam's razor says that the most truth-conducive hypothesis is the simplest hypothesis, right? And this is an important principle in ML because oftentimes an overfit model performs worse than a better fit model that doesn't fit to the noise of the data, right? A simpler model is a better model, right? That takes signal and data. But sometimes the problem with this is that the simplest isn't always the fairest, right? Where just concerning the data, we might perpetuate past injustices. And the data might not give us the whole story that we need. Because there's a tension here between faithfully reflecting just the data, right? Whether we want to faithfully just reflect the data using ML, or whether there's an obligation, a further obligation to kind of question the data and design systems that conform not only to the data, but maybe to some notion of equitable behavior that might not be present in our data, which is kind of the motivation of fair ML, right? And so there are examples where this might happen. A couple examples that you might pick up on that I'll just go through here is that data might have historical trends, right? Or embedded things, historical trends that are embedded either sociologically or just like in a certain context, right? Where historical data that you feed into some ML algorithm might be discriminatory for sociological reasons or reasons that are deeply embedded in some context, like some workplace or some specific decision-making scenario that you gather data from, right? And for instance, like if we're doing resume screening or job hiring for some company, right, that was previously biased towards men because maybe the past managers or past teams of that workplace or past company culture, et cetera, right? We might create a gender biased algorithm because that algorithm just wants to fit to the data, right? And there's nothing really in the data, kind of like in that riddle of induction, kind of that kind of gives us that alternate hypothesis that there might be some historical trend, right, that is influencing the data that we might not want to pick up on. And yeah, so this is kind of related to that problem in induction, right? That by just trusting the simplest signal in the data, we might create an unfair predictor. And if we're interested in doing fair ML, then we need some way to kind of sniff out these historical trends in data or discriminatory trends in data that we might not otherwise have picked up on if we're just looking at the data itself. So also things that have, or another scenario that has kind of gone a little bit of flack is like nonsensical trends in data. Sometimes the simplest signal just might not be, just might be a nonsensical signal, right? By coincidence or otherwise, right? And one paper that recently generated some heat is that a paper claimed to predict with very high accuracy the criminality of individuals over their portraits. This is an example over here. But it happened to be in a rebuttal and to that paper and a further examination that it was just picking up mostly on whether individuals were frowning or not in their portraits. And this is one thing that facial recognition systems might be particularly, I guess, weak to, right, is nonsensical trends in the data, where the simplest trend in the data obviously might be unfair or undesirable if this was actually deployed in some criminality algorithm used in maybe like predictive policing or something, right? And finally, probably most importantly, is that ML systems in fair ML also often create a closed loop, right? I think it's often tempting to kind of create ML systems and think of it as just a pipeline from training to test to prediction, right? And that's it, right? But often they form a closed loop because many of the systems that we think about when we think about fair ML systems in fair ML often have to do with human scenarios where I guess it impacts like the human decision-making on like various aspects that might impact the data and the world that they're trained on, right? So for instance, look at recommender systems, right? So when you're browsing around the internet and I guess you click on an ad, right? Then that ad reinforces that you like thing, I don't know, like clothes of some certain sort, right? And that becomes more trained data in your own profile, right? So things like that, feedback loops, and ML systems that are for high stakes decision-making scenarios that are deployed in large scale also impact, right, the humans that they're trained on. And that might become data for further use, right? And this feedback loop can't be just found by just looking at the data itself, right? By just observing the data and performing a simple induction, right? Or prediction. Just looking at the trained data and predicting from that, we might not pick up on these feedback loops, right? It takes a further step back to look at the whole ML system, right? And the whole loop that it kind of subsumes, and look at how that loop kind of impacts itself. All right. And if this isn't clear, like one example is like predictive policing and crime locations. It's a pretty well-known example. So like a predictive policing algorithm might use arrest records, for instance, as a proxy to predict location of new crimes. And then use these arrest records to determine police deployment as a feature. And so increased police deployment in certain areas obviously increases surveillance in certain areas, and obviously might increase arrest records in those same neighborhoods, right? And so if those neighborhoods were already...
Hello, seems that we lost the speaker for a few time.
I'm so sorry, everyone. My internet cut out midway. Were we on, I think, the slide, right? Before it cut out? I'm not sure what time, but I think I got disconnected here. So yeah, so I'm just going to continue on this slide, almost at the end of it. But so yeah, this is the last blind spot that we're going to go over, measurement. And this is in particular important to philosophy of science as well. And there are multiple theories of what of measurement in the philosophy of science, right? And one of the most prevalent ones is the representational theory of measurement, RTM. We're going to say for short, right? That basically says that measurement is a mapping or construction from empirical structures to formal structures. And these mappings are known as scales, right? And how we measure things. So for instance, the measurement or the scale of longer than, the mapping of longer than between things is an example that's pretty easy to go over, right? Suppose that we have like two rods, A and B, and we want the empirical relationship of longer to be mapped to some formal structure, right? And so we might say that A is longer than B if like when one end of the rods are flush with the others, or with the other, then A extends past rod B, right? And so we say that A is longer than B if that's the case. And we kind of have to like, it seems wordy to just put the idea of longer into this representational theory of measurement, but like that's, I guess, one of the jobs of looking at measurement from the perspective of philosophy is to kind of well define these things. But the important thing is that whenever we measure something, right, we at the center of this, there's an assumption, right? And for the rods, it's like that the rods are flush to each other. But for other measurements, right, there are always assumptions, right? And assumptions sometimes are often harmless, right? How else would we measure rods or wooden rods or whatever? But a lot of measurements might not have these harmless assumptions, right? And there are a lot of interesting questions that come from measurement that are metaphysical or epistemological and semantic that we're not going to go over today. We're just going to go over assumptions that are at the center of measurements, right? Because in ML, right, the data that we have, the data that we're given as an ML engineer, right, we're given a bunch of data and it's ground truth, right? So for practitioners that might be on in a job where they just deal with ML on a day-to-day basis, right, there's not much room for questioning there, right? Data is just kind of given as numerical ground truth. And domain experts are often not there to operationalize or make explicit assumptions that are made in the feature, right? It's just up to the engineer to predict using the features that they're given. But something that Moritz Hart said in Europe's talk in 2017 is that every feature is itself a model when it comes to fair ML, right? Because in fair ML, a lot of the concepts that we're interested in measuring are empirical concepts that are related to humans, right? And this is very tricky, right? Because fair ML is usually concerned with the human domain. We're usually formally measuring a lot of elusive things and including those measures about those features in our data. For instance, can intelligence be measured via an IQ test, or communicability be measured via a writing sample or an interview or whatever, right? These are often just presented as numbers or scores that we might crunch into an algorithm, right? And so, yeah, every feature is a model. And this also has to do with outcome variables, right? They're treated as numerical truth. And so maybe we might think of fairness as starting much, much earlier than even the definition or creating the algorithms. It might start even at the stage of collecting the data itself. And a lot of this data, we might not have any idea how it's collected, right? So yeah, there are two kind of things to look at here, right? It's the features of the model, right? So features, like Maurice Hart said, right? Like every feature is a model, and many features that ML pipelines kind of take for granted are themselves measurements that incorporate their own assumptions, right? Are themselves kind of models, right? And features incorporate a lot of important normative or subjective context-dependent assumptions about their measurements. But any ML engineer like on the job has to treat them kind of as numerical truth, right? So for instance, things like IQ tests on IQ, like we said before, IQ tests kind of assume normatively that it's a good stand-in for intelligence, right? Or written samples might introduce reader bias, right? Or scores on written samples or recidivism scores that are used from the Compass algorithm might be used further down a pipeline to predict parole and sentencing and things like that, right? And so these features, it's important to understand that like they're all measurements in themselves, right? And things like maybe like height and weight, right? Or eye color might be obviously more objective, but there are measurements that are on a varying scale of like subjective when it comes to humans, right? And this isn't just the features, right? It's every part of kind of the data, right? And this also applies to the outcome variables, right? So in a lot of supervised learning settings, many labels themselves are constructs created only for the purpose at hand, right? So credit worthiness is a construct created by credit lenders, not an intrinsic property of humans themselves, right? They're context dependent based on a specific credit lender's need, right? Credit worthiness in one agency might not be the same as credit worthiness in another, right? Another might be a good employee score at some hiring, for some hiring algorithm at some workplace, right? A good employee score might incorporate all the biases that are prevalent in, I don't know, previous workplaces or managers, teams, et cetera, right? Because good employees in those past cases might have just been good employees based on maybe something discriminatory or sociologically discriminatory versus certain groups, right? So yeah, a good employee score might incorporate all those biases as well, right? And these constructs are often used at the end of the pipeline for a lot of ML algorithms, right, as ground truth as well. So yeah, in both cases, context is crucial to kind of understanding the measurements involved because training data is often given to you as ground truth. And of course, there are no current approaches to somehow encode context or how these things are measured, right, into ML features or labels themselves, other than, I guess, maybe good documentation. But yeah, that's another blind spot that might be good to look out for. And so yeah, finally, that's this last slide, the conclusion. Because I got disconnected, I'll just go over this very quickly and just recap. So we've now shown kind of 3 methodological blind spots in ML fairness from the perspective of philosophy. These all kind of stem from the assumption, first of all, that fairness in fair ML is a context-sensitive value in value theory. And because of that, it avoids capture through methods that simply specify some one-size-fits-all definition of fairness, or which is like abstraction, or assuming that we might have well-measured data, which is the blind spot of measurement, right? And so abstraction, again, is kind of realizing that the question of like what is fair is yet unsolved, and exporting fairness kind of contradicts with context sensitivity, right? Plugging and playing something that's fair further down a pipeline, just assuming that it's just fair in general, right, is often harmful towards other parts of the pipeline. And so induction is taking the simplest pattern is not always the fairest pattern, right? So I guess inspired by just the basic problem of induction in the philosophy of science, we might look at induction in fair ML and see that the information that we want is not always just in the data. And sometimes we might want a GRU hypothesis, not a green hypothesis, emeralds or green hypothesis. And for measurement, the idea is just to take a closer look at the measurement of data and how true ground truth really is, right? That the features and the outcome variables in your training data that end up creating your model, right, might be measured in a very wide spectrum of subjectivity and objectivity, right? Something as objective as like eye color or height or weight might be part of the same feature set as things like intelligence by IQ score or hireability or communicability, right? And finally, why philosophy, right? The whole point of this kind of project was just to look at things in fair ML from the philosophy standpoint, because in the end, one of philosophy's biggest strengths is just to revisit really basic, it seems like taken for granted assumptions, right? And to kind of poke at them and kind of avoid losing the forest for the trees, right? To avoid getting tangled up in the implementing and the designing and making the ideas for fair ML without kind of taking a step back and looking at the assumptions that we might be making when we're doing those things. So yeah, that's pretty much it. Thank you for listening to that. And I'm sorry. I'm so sorry for getting disconnected. My internet is a little wonky nowadays, but that's pretty much it. Thank you so much.
Thank you very much, Deng, for this very interesting talks. So now we'll move to QA. We have some exciting questions. I will start with the first without further notice. The first question is from Nadim Abbas, who is asking, as we have a number of different machine learning algorithms, which can be classified in different groups, such as supervised, unsupervised, Bayesian, he wonders whether the issue of fairness applies equally to all types of algorithm, or whether or not there are certain specific type of algorithms that are more sensitive to fairness than others.
Cool. I just click answer live.
Yeah.
I think, okay, cool. So yeah, thanks for the question. So actually something that's interesting is like a lot of the ML fairness literature as of right now is still focused very, very much on like supervised learning. And so a lot of the fairness definitions I gave in the earlier slide, there's a big chart over, I'm not sharing anymore. I thought I was sharing still, but there's a big chart of fairness definitions. Most of them were just in the supervised setting, and a lot of the work has been done there. I think there are a couple surprising works in the unsupervised setting for now, but I think that's mostly the focus. As for like the problem, in the supervised setting, it seems, I guess, most natural because the idea of fairness in supervised setting might seem most natural right now, which is probably why like a lot of the literature is on that. Yeah, it's like, I think still on the way to expanding to like different settings while we first tackle this first one in supervised. Yeah. Okay. And do you think types of algorithms are more sensitive to fairness than others? It's an interesting question. I think most of the algorithms that have been like exposed in the media are typically actually pretty basic algorithms. Like a lot of like compass and stuff like that were just like regression algorithms that people use because they're also they're also like relatively old. But I think fairness in other like settings or other classification algorithms are also being examined as well. They're mostly being examined kind of in a black box because a lot of the methods for fairness are like pre-processing methods where they're kind of algorithm agnostic, or like post-processing methods that are also kind of algorithm agnostic. So yeah, if you're interested in looking at that, then like, yeah, there's a lot of surveys of that kind of stuff online of pre-processing algorithms and post-processing algorithms. Yeah, but yeah.
Okay, thanks very much. So we have another popular, exciting question from Gopi from Queen's University. He's asking if you could provide an example of a case where a mathematical definition of fairness fails to translate to real-world examples in the context of machine learning modeling.
Okay.
So in the talk, you mentioned that during the translation, there is some loss of abstractions.
Right. Yeah. So I think I gave the example of like false positive rates, or I could give an example of demographic parity, for instance. That's an even simpler kind of fairness definition. So demographic parity, I think, was probably like one of the first definitions of fairness that kind of came out. It's also called like statistical parity. There are a lot of different names for these things that kind of basically say the same thing, right? But it's basically saying that the probability of a certain group being classified as a positive outcome is the same as another group being classified as a positive outcome. So for instance, in like some hiring problem, maybe if we're just doing binary classification on them, then maybe males have the exact same positive rate outcome as females in that hiring problem, right? But there's like something lost there because it doesn't seem intuitive that the only thing that we want to do to make, I guess, a hiring problem fair is to equalize the positive rates, right? because there's some pretty simple stuff that you can do to do this, right? So like if you want to equalize the positive rates, right? And there are actually like many less qualified male individuals than female individuals or something, right? Then you might just, like your algorithm might just pick a bunch of.
It seems Samuel has been disconnected again. But he's coming back. Okay.
Oh, sorry, I got disconnected again.
Yeah, okay.
But yeah, like I was saying, like, yeah, demographic parity itself seems like a kind of a blunt measure of fairness when all we're trying to do is just equalize false positive rates, right? And yeah, and then at that point, like, there's also issues about accuracy, right? Because there's a trade-off here between making a classifier more fair and.
Okay.
Just like I said before, like from a certain group, less qualified individuals based on the other features, right, to your model. So,
okay.
Yeah.
Okay, thanks. Let's maybe pick a couple of more questions before we can end the session. In any case, we will email you all the questions that
sounds great. Yeah.
So that you can respond to them, and then we will publish them on the SEMLA website. So we have a question from Futse Yugo, who is asking, what about the bias introduced during coding, right? Like a specific developer has a specific philosophy and suggestion on thoughts on how to handle it. Like, what do you think about that type of bias? Not in the data, but mostly in the implementation.
Right. Sorry, I'm trying to look at where this question is.
It's...
Sorry, can you repeat the name for that one again?
Futse Yugo. It's on the top. The questions are words, and then it's on the.
Oh, seems like I can't see that one. Yeah, maybe if you just repeat the question one more time.
What about bias introduced during coding, roughly?
Oh, I see. Okay, that's
whether
that's
there is any bias introduced during
coding. Right. I think that's an interesting question because like it's on the side of like the software engineer or ML engineer. So yeah, a lot of like the techniques, I think that's actually like itself like another blind spot that people haven't really talked about, right? A lot of the techniques currently are just like mitigating bias that has to do with like the data set that you're given, right? And things like that. So I was actually on a project that investigated like a field. The idea was that we did a field experiment on a bunch of ML engineers. And I could actually link to this paper later, but the point is that we wanted to actually see like, for just ML engineers that had like a simple regression problem, I think that had to do with hiring, whether they exhibited any natural biases just implementing the algorithm against, I think, gender bias or like racial bias on this kind of hiring data set. And yeah, what we found is that like there actually wasn't. It was like a sufficiently like diverse kind of group of people, of like a pretty big group of engineers, I think around 400. But yeah, what we found like was that there isn't any bias like introduced directly from like the demographics of programmers doing that kind of stuff. But yeah, there's not a lot of work in ML fairness that kind of deal with like from the perspective of the programmer or the person actually implementing the algorithm. So I think that's actually a pretty interesting direction to look at further.
Okay.
Yeah.
Okay, cool. Maybe take it. So another question from Huda Kadui. He quotes, even with perfect sampling and feature selection of data, we still face historical bias. Right? So historical bias is fundamental structural issue, the first step of the data generation process. Right? Could you comment on how to deal with this particular issue when addressing fairness? How can we handle this?
Okay. Yeah. So yeah, that's definitely true, right? That's part of what I said in the other slide about induction, right? Is that historical trends in data might exhibit biases that we want to maybe avoid, right? And so yeah, I guess it's not even that. So for instance, if you just have all the data from like a workplace and you're doing a hiring algorithm, and in that workplace, right, in all the past years from like the beginning of when that job was made or like when that company was founded, like it was discriminatory against some certain population, right? It's more that there's like this in fair ML, I guess, there's this motivation to, despite how perfect that data might be sampled, because that data might be perfectly sampled, because the distribution itself might be biased, right? We still want to mitigate kind of this long run, I guess, these long run fairness issues in that data set or that specific context, right? And so, yeah, most of the, I guess, methods in ML fairness right now do kind of address that directly. Like, so like they kind of assume already that the data set you're given might already be biased like historically. And so all of them are kind of agnostic in that sense to that kind of already existing historical bias in the data set. For instance, like a very simple pre-processing algorithm to kind of mitigate fairness that's used currently is like one called like reweighing, where all you kind of do is just reweigh examples such that when this transform data set is fed into your classifier, you kind of satisfy one of these fairness definitions, right? So despite the original distribution of the data, right, you're trying to kind of modify it so it is fair. So in that sense, yeah, that's how you kind of combat that.
Okay, so we have many more questions. So what my suggestion would be, we'll email you the questions, we'll correct the answers, and then we'll publish them on the website so that everyone can have access to the answers to the questions. And maybe I'll ask my one final question before we conclude the session. On the software engineering perspective, what would be your recommendation for engineers trying to bring into production ML-based system, right? What do you think should be the, let's say, top 2, top 3 things to do to handle fairness? Like, what would be your recommendation on the SE perspective?
Right. Yeah. So I actually was originally going to give like a couple really broad suggestions at the end of the presentation that at the conclusion, but I guess I'll just talk about right now. But like, yeah, at the software engineering level, right now, I guess it's currently, obviously there are currently steps like actually using, there are like already algorithms and methods that are, like I said, at all steps of the pipeline, like pre-processing, in-processing, and post-processing that are available like publicly, like on GitHub and stuff like that. Or like, I think IBM has a package that's called IBM like Fairness 360. Microsoft also has a package, things like that. There's like growing actual implementations of ML algorithms that are found in research in the fair ML literature that are already like implemented and kind of ready to go. But yeah, like I think the awareness of it is kind of like the point of this talk. So I'll just talk about like really high level kind of solutions that I might see. So like suggestions, I guess like one is like abstraction, and like we talked about abstraction and kind of measurement in fair ML. They both kind of require a better, I guess, oversight from individuals that might have a better understanding of how to measure normative assumptions or kind of measure things that are just based on these elusive concepts that human beings might have, like intelligence or like communicability and things like that. So some like, I guess, incorporation of like social scientists or like sociologists or lawyers and stuff like that into like the pipeline of building these like really high stakes decision making kind of algorithms might be important, right? And so obviously that depends like algorithm to algorithm, right? Like you're not going to be doing that for like something that's just predicting, I don't know, whether things are dogs or cats, right? But like if your algorithm, I guess, is going to be used for something that actually might have a broad societal impact, then it might be worth like looking into just adding more input from domain experts in all parts of like the ML pipeline, from design to otherwise, right, to deployment. Yeah, and so yeah, at the small level, so that's like at the large level, and at like the small level or like the zoomed in level, like as a software engineer when you're doing it itself, like yeah, just I guess the paying attention to these kinds of issues that they're in the data set, that they're in the ML pipeline themselves, could be helpful. And just kind of like taking a closer look at like, what is the data that I'm doing? What is the data that I'm predicting on, right? And what is the data I'm training on? And being aware that like, this is kind of like a growing field that already has like some implementations already out in the wild that you could look at. So yeah, I could also link to those that have been implemented by like Microsoft and IBM and like other companies. But yeah. If you look at all like major kind of tech companies, they're kind of also already tackling this issue as well in software. So yeah.
Okay. Thank you. Thank you very much. Thank you everyone for attending. Thank you. Bye.